opposite direction compared to the rotational direction of the flow. So if you represent it from the front, so you have the shaft, so you have the blades, the different blades that are here. So you have a pocket where you create the problem. So let's say you have more blades like this. So this pocket is on one blade. For example, it could be on two blades because you have two stones, or you have a big stone. I don't know what you can imagine. And you will have the problem that will grow like this. That could grow also like this, but at a certain moment, the problem here will be not anymore existing there, and the problem will grow like this. And then the problem will disappear here, and the problem will be already only there and growing like this. And you see that this pocket is rotating compared to the rotation direction. You will have the rotating stall speed that will be going into the opposite direction compared to the rotating stall of the compressor. And so the problem is coming back where it has been created. So vroom, 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 it's rotating like this. Of course, you could have maybe two rotating stall cells. You could have two rotating stall cells, one created there and one created here, one rotating in this direction, one rotating in this direction, opposite to the rotation direction of the system. You could have also three pockets. I don't know what you could imagine, different systems. Normally the pockets will be in a kind of equilibrium, because you see that the problem is balanced, because it's always coming back at the same place. And so if you have two pockets, normally they will be at the opposite position, because the problem is balancing itself naturally. If you have three, you will have one there, one there, one there, at 120 degrees, roughly speaking, about compared to each other. So, and what is the consequence of that? What is the consequence of that? We understand, okay, there is a stone, a flying, I don't know, a bird, I don't know what, disturbing the problem, disturbing the situation on the blade, and the blade is seeing this rotating stall. Is it a problem? What are the consequences? Is it a problem? In fact, we see that this is always a very small problem. You see that it's a problem over a certain radius only, and over, let's say, one blade or two blades or three blades. It's related with m dot, a very small problem. So you see, I've taken this example of course we can say about everything about this example. What do we see? 100% of the flow. How many of these percentages are influenced by the problem? Let's say 0.1% here, or 0.2, 0.2, 0.2. 0.2 for this section. So that means 0.6%, 0.6% of this ring. So a very small quantity. Will the compressor see something? Will the pressure here decrease? Most probably not. Yes, maybe 0.0, very small difference, but impossible to notice that. Globally speaking, mainly the system is moving, the pocket of the rotating stall is moving, the rotating stall cell is rotating, is moving. You will not see any effect at the level of the performance of the compressor on the compressor map. The pressure ratio will not change, m dot will not change. What is not passing here is passing there, is passing here. So globally speaking, the influence will be very, very small. And even if you have two pockets or three pockets, so the perturbation of the performance of the compressor and also the performance of the engine will be very limited. But mechanically speaking, it will be a problem because this blade that is at the origin of the problem, or another one, because all blades are becoming the same with an impact of the stone or not, this blade is working in a right condition, rotating, 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 and at a certain moment, the rotating store cell is coming, so it's rotating, the rotating store cell is coming, and hop, impacting this blade, and then leaving. But this blade will see back this rotating store cell later on. And so many times per second, with a frequency that is depending on the rotational speed, you will have the velocity triangle on the blade that will be changed. And what will you see if you take the loads? On the blade, normally you have something that is, let's say, a constant load. There is a constant load that is, let's say, related to the pressure you have, the mass flow rate you have, the rotational speed you have, centrifugal stresses. I don't know what you want to express by this. So let's say this is sigma in function of time. And in a steady state condition, the blade is always rotating at the same rotational speed, always seeing the same m dot, always seeing the same speed of the flow, always seeing the same delta P over the suction side, pressure side, etc., always the same rho. So you see a constant load in steady state. And due to this perturbation, what's happening, you will have something like this. Hop, and then it's disappearing, and then coming back. It's the same, of course. So the same. And then coming back. And what you see, you will have an increase of the load at some specific moment. Each time that this rotating store cell is coming. You have an increase of sigma, it's bad, but mainly the problem will be the frequency. It's related with the rotational speed. If the rotational speed is, let's say, 20,000 rounds per minute, 20,000 rounds per minute, and if you have, let's say, 2 cells, you will have 2 times, so 40,000 times per minute, 40,000 times per minute, so you will have 40,000 cycles per minute. And what is the danger? The danger is that you have, in fact, high cycle fatigue. That means that when you are taking the variation of the stresses in function of the number of cycles, you have a curve that is for a given material, at a given temperature, you have a curve that is like this, with here what we call the sigma infinite. If this delta sigma is larger than this one, you will come here. And maybe here, this is, let's say, 10 to the power 6 cycles. 10 to the power 6 cycles, if you take 10 to the power 6 divided by 4 times 10 to the power 4, this is this. 100 divided by 4, this is 25 minutes. And in 25 minutes, you will break the blade. So this is a load, but if you have a cycle here that is, let's say, here, at that time, this is something that is a load. Of course, you need to check if this is indeed the case. If the perturbation is becoming too high, maybe you will be in this case. If the perturbation is low, you will be in this case. But globally speaking, there is no problem from a performance point of view for the compressor, but you can have a mechanical problem that you solve by different design circumstances, selecting a better material, reinforcing the material by laser shot peening or things like that. And globally speaking, normally if you take the right materials, reinforcing the materials, doing the right analysis for being able to work with these rotating stores, cells, 1, 2, 3, 4 in the compressor, this is totally allowed to have a problem like this one. And that's why you will extend the zone. Of course, I have not yet explained why I have only indicated this in the low rotational speed region. I have not yet explained that. It will come back later on. I'm just explaining the principle. But in fact, the situation could, let's say, degenerate. It's possible that the situation could degenerate. So what could lead to a degeneration of the situation? There could be different reasons. Let's say that you have still the same blades that I have shown before, so always the same blade. And instead of sending, so I have my W here, I have here my angle of attack, and I'm sending, so let's say 3% of my total flow here in between, 3% over the whole let's say thickness. So what's happening? If I have now not anymore due, let's say that the blade is also impacted by a stone, becoming like this, but what's happening if the fact that the angle of attack is increasing is now leading to a situation like this, which is what is called a leading edge separation instead of a trailing edge separation. At that time, the blade is separating from the trailing edge, from the leading edge. And you see, if the blade is separating from the leading edge, the throat will become much smaller than, where was that? Here, in this case. And instead of ejecting, let's say, maybe it's not exactly coherent with the value due to my drawing, if I'm not ejecting 0.1, or I was saying 0.2%, so I was ejecting before 0.2%, having 2.8% passing here. If I'm not injecting that, but only accepting here 1%, and so 1% here and 1% there, then I'm changing more abruptly the situation. And what will happen? I will separate a larger zone in the blade, and also looking at the zone that is impacted here, I'm representing that on another blade. I will take a much larger region, maybe even a region like this, because I have too much flow rate that cannot pass here. And so I have to send too much there, and on this blade I will also have a leading edge separation, and so also 1% only able to pass here,